In this video, we're looking at solutions. You should already be able to explain the general trends and solubility of solids and gases and define saturated, unsaturated, and supersaturated solutions, though we will review it. But by the end of the video, you should also be able to explain solubility in terms of intermolecular forces of attraction, draw particle diagrams representing the saturation of the solutions, and then calculate concentration using various units such as molarity, molality, mole fraction, percent, and parts per million, which is also a review from last year. So the question of the video is, how does this work? So we've seen something like this before. So my question is, how is this occurring if you're only adding one small crystal? How can many more, it seems to be growing, right? So let's talk about what a solution is. Solutions are homogeneous mixtures of two or more substances. We can't see the parts with our eyes, but if you zoom in, they're a nice patterned material where it looks like repeating particles over and over, very evenly mixed. In a solution, the solute is dispersed uniformly through the solvent. The solutions, the intermolecular forces between the solute and the solvent, must be strong enough to compete with those between the solute particles only, like solute to solute, and those between the solvent and solvent. If they didn't compete, the solute would stay solid, and the solvent would stay its own particle. So for example, the sand must have really strong forces of attraction, or bonds, that makes it so it does not want to dissolve in the water, even though the water has hydrogen bonds, right? So there's no interaction between the two, so their interaction is less than the interaction between sand and sand, or water and water. So the types of solutions we can get are saturated. Saturated is when a solvent holds as much solute as possible at that temperature. We should know that if you increase the temperature, it probably dissolves more, so we want to keep the temperature the same. The dissolved solute is in a dynamic equilibrium with the solid solute particles. Some may dissolve, while others will precipitate, but every time one dissolves, one other particle precipitates somewhere else in the solution. So it looks to the visible eye like nothing's really happening, but on a particle level, there's a lot changing. That's why we say dynamic, it's moving. Unsaturated means there's less than the maximum amount of solute for that temperature in which you're dissolving the solvent in the solvent. And so this would be when you have like weak iced tea or something like that. But what we just watched in the video is a supersaturated solution. The solution looks the same as a saturated solution, but it's actually holding more than it should. And the only way that happened was because we had heated it up, added all that would dissolve at that hot temperature, and then cooled it back down, and now it's unstable. When it's unstable, the crystallization can be stimulated, crystallizing any excess material using the seed crystal as we saw. You can also just scratch the inside of the flask or move the solution a lot, and it will crystallize out. If you remember in the heat pack lab we did last year, that was a supersaturated solution. Looked like it was all dissolved, and as soon as you clicked the little button, it all solidified and released heat. The factors that affect the solubility was whether the substances are the same polarity. Polar dissolves polar, and nonpolar tends to dissolve nonpolar substances. So the solubility of gases in water increases with increasing mass. The larger molecules will have stronger London dispersal forces, and so they'll dissolve a little bit better because they have stronger forces, more like water. So in the example you have on the right, I have the gases in order of increasing mass. Nitrogen weighing the least, and it has the least solubility. Krypton weighing the most, and it has the most solubility of the few that I've listed. So as the force increases, it dissolves better in water, which has an increased force. The solubility of liquids and solids does not change appreciably with pressure, but the solubility of a gas in a liquid is directly proportional to its pressure. The more you push the gas in, the better it will dissolve. So if you think about soda, soda is capped at a high pressure in order to keep the gases stayed in the soda as it's being transported. Generally, solids increase in their solubility as you increase the temperature. The hotter a substance is, the more it dissolves. Like hot coffee dissolves more sugar than cold coffee, and the same with tea. But for gases, it's quite the opposite. Gases dissolve less as it's hot. Think again about soda. If you heat soda up, all the gas bubbles come out. If you cool it down, the gas bubbles stay in and it will stay not flat longer. So if you think about soda in two different conditions, soda on an airplane looks particularly fizzy, and that's because you're flying high, it's low pressure, so the gas can come out, and usually it's not particularly cold. It's usually pretty warm on the plane. But if you have soda chilled, you can notice that there's visibly less bubbles in the soda because it's colder, so the gases tend to stay in. And you're probably, in this case, not on a plane. So in that case, you're maybe at a regular pressure or even a heightened pressure, and it's keeping the gas bubbles in. Let's talk a little bit about how you can calculate like exactly how many gas bubbles are in your soda or anything else, sugar in a solution. The first way that we usually do is moles per liter. Remember that it just has to be in those units. So if you had a question like, calculate the molarity of a solution dissolving 202 grams of KNO3, its molar mass was given just to be nice, in 250 milliliters of water, we would divide the two masses to get the moles, and then divide those moles by the liters of water. So notice I changed the 250 milliliters to liters, and we got a 4 molar solution. Something we should know about molarity is temperature dependent. So if it's hot, it will kind of change the amount of water you have. The water might expand and therefore decrease your molarity. And if it's cold, it might contract a little bit, which is why when we do these labs, and I make all our solutions in molarity since it's the most common way to make your solution, we have to do the lab kind of right away because otherwise the molarity of the solutions might change. Molality, though, is not temperature dependent. If you look at it, it's moles per kilogram of solution. The kilograms or the mass of the substance shouldn't change by changes in temperature. So in that case, we can maybe do the same exact calculation, but do it for molality. So first, again, we're going to do the 202 grams of KNO3 divided by the 101.0 grams per mole, and say that we still have 2 moles. But the kilograms of solution has to be the mass of the solution, the solute, and the mass of the water together, right? So we got our moles. We have to add the solution and the solute together. Notice I changed the water's milliliters to grams because its density is 1, and I added them together and then changed it to kilograms. Now I can divide, and you'll see that the molality is slightly different than the molarity we had before at 4. So these are two different values because they're two different ways of measuring the same solution. We can also use mole fractions, which we saw on the gas particle topic, where it's the moles of the solute per moles of solution, or the moles of the solvent per moles of solution, and the solute plus the solvent moles should equal 1. We reviewed it enough in gases that I hope it's okay now. And last year we also talked about the differences in percents and parts per millions. So in any type of percent or parts question, you're always going to do the amount of solute on the top, usually in grams, divided by the amount of solution, again, usually in grams, or maybe it's milliliters per milliliter, but the unit should be the same. And then you're going to multiply by what its representative quantity is. So if you're talking about parts per 100 or percent, you're going to be doing times 100. If you're doing parts per 1,000, it'd be times 1,000, parts per million times 1,000,000, and so on. The reason we have so many different types is because if you have a large quantity, you only have to do say how many parts per million parts, right? I'm sorry, 100 parts. But if you have a very small quantity, like you're talking about smog in the air or something like that, you're going to be talking about parts per billion. That doesn't mean it's good or bad. It just means that you have a small quantity, and even that small quantity can be pretty deadly or toxic. And if it's particularly small, it can be measured in parts per trillion. So the reason why I thought it was interesting was because you see this graph quite often. In fact, I saw it when I went to the San Diego Zoo. They had this graph, life size, where the current level of carbon dioxide was 2 times the size of me. Pretty neat. And what it's showing you is that years before today, we did have changes in the CO2 in parts per million. So the CO2 was, 200 or less than 300 parts in a million parts of nitrogen and hydrogen and helium and oxygen that are in the air normally. And it changes cyclically, and we do see that until we get to the Industrial Revolution. Once that started happening, we started seeing a complete spike that we never saw before. And the way we know this was by, ice core drilling and stuff like that. Just figure out how much CO2 was in the ice before, as it was freezing years ago, however long. And so because the amount of CO2 in the air is really small value, we measure it in parts per million. But does that mean it's a very small effect? No. the more CO2 we have, the hotter these temperatures seem to be, and the more we have ice caps melting, or more we have changes in how many forest fires, dryness and wetness around the area. We're having more tornadoes, more hurricanes. I don't want to get too political here, but I think it's definitely such a small value, parts per million, can have just a dramatic effect. At this point, you should be able to explain solubility in terms of intermolecular forces of attraction, draw particle diagrams representing the saturation of solutions, and calculate the concentrations of molarity, molality, mole fraction, percents, and parts per million.